Hello and welcome everyone to our last day of Research in Options Rio 2020. So it's really a pleasure to have you all here. We are um, very pleased to announce that we have over 800 participants in our meeting, and we had quite a number of people attending throughout the day yesterday. We expect the same numbers are going to be running today. Let me start with some announcements concerning this session. The session today is sponsored by Diamond Investments, and we are very thankful to them for their support. This is going to be very helpful to support future events as well. This also, the other thing I'd like to announce is we are going to have some group pictures taken during the coffee breaks. So if you join us in the coffee break, you might participate in the group pictures there. Finally, and last but not least, let's get to Professor Jim Gather, who is going to introduce our next speaker. So, Jim, please, the floor, or perhaps the screen, is yours.
Okay, thank you, George. It's my pleasure this morning to introduce two speakers on quantile modeling. The first of these speakers is Andrea Macrina, who I've known for a long time. I meet him all over the world. I think we met in Australia, we met in Japan, we met in London, and I wonder which language he's going to present in. I guess English, because he speaks English, German, French, and English, according to his resume. So anyway, let me not take any more time. Andrea is very well known to most of us, so he doesn't need much more introduction. I'm very excited to hear what he's going to say about quantile diffusions. Over to you, Andrea.
Thank you very much, Jim, for this very kind introduction. And thank you very much to the organizers for inviting me to participate in this wonderful conference and for running it also in a very difficult year. I'm really grateful for being able to report today on some joint work with my PhD student, Holly Bernally, and my collaborator, Gareth Peters of the Heriot-Watt University in Edinburgh. The paper on which this presentation is based is available on arXiv, as you see here, and I carry forward the link on each page in case you miss it at this stage. So today I thought to give a very brief introduction before I go on to the construction of quantile diffusions. And after, I will show a class as an example of quantile diffusions based on the Tukey quantile transform. As an application of the many that we envisage to pursue, I'd like then to focus on measure distortions and how these can be induced by the quantile diffusions we develop. And I shall finish this presentation with a research outlook and references. The motivation for this work lies with two main reasons for constructing quantile diffusions. The first is to actually generate stochastic quantile dynamics. And the second is to produce stochastic processes that are able to encode statistical properties, relative statistical properties, such as higher order moments, for example, skewness and kurtosis. Our focus is on obtaining a recipe for the explicit construction of quantile diffusions. And we will begin with introducing a diffusion process, a general diffusion process, with marginals distributed according to a function f of y. However, we will not define the quantile diffusion processes in terms of the inverse of the law of the process y. Instead, in one of the two proposed constructions, we will consider a composite map that is reminiscent of rank transmutation maps, where the quantile function z will be given in terms of a generic quantile function q applied onto a generic distribution function f. Quantile processes have been considered in statistics and probability, econometrics, operations research, and other areas of science. And thus, there are several definitions and characterizations of quantile processes, depending which area one looks in. And these definitions and characterizations may include empirical quantile processes, alpha quantile diffusions, and conditional quantile autoregressive processes as examples. The approach we propose is most related perhaps to works by Akahori, Dacios, Embrechts, Rogers, and Yor, but also Miura, Steinbrecher, and Shaw, and of course, Tukey. Before we define the building blocks for the quantile diffusion processes, I remind the definition of the generalized inverse as given in the paper by Embrechts and Hoffert of a few years ago. So for an increasing function f that maps from the real line to the real line, with limits of x to minus plus infinity given as the function of minus infinity and the function f of infinity, the collection of generalized inverse functions being the map from the real line to the extended real line is defined in terms of the infimum that you see in equation 1. The convention is that if the infimum of the empty set is equal to infinity. Thus, we can use this definition to introduce the quantile function, where we consider a random variable x, real valued, with distribution function f of with sub x, denoting that this is the distribution of the random variable x. That maps, of course, from R to the unit interval 0, 1. Thus, the corresponding quantile function of the random variable x, denoted by q sub x, is a map from 0, 1 to the extended real line. This takes us now to the construction of quantile diffusions, and we consider two types: the random level quantile diffusions and the function valued quantile diffusions. In the paper, we produce actually some cases where we identify the link between the two constructions. So to begin with, I'd like to now define the random level quantile diffusions. The first thing we do is to consider a diffusion process y. Then we take a quantile function denoted by qz, where little u is the quantile level taken with values between 0 and 1. There are two cases, two subfamilies. One where the process y, the driving process, is governed by a time-dependent distribution denoted by f of sub y t comma y, and which allows then to create a process u of which marginals are uniformly distributed. This process u is crucially constructed by taking the law of the process y and applying it onto the process y itself. We call this case the true law case, since the distribution f is the law of the process y itself. The second possibility for constructing a random level quantile diffusion is to consider a generic distribution function f, and to then construct a process u tilde that takes values that maps on 0, 1, but that is not uniformly distributed. So the law of u tilde is not the uniform law. This is where we call the function f as the false law of y, because that is not the law that y comes with. So now we can produce the two cases, the two definitions for the quantile diffusion that has a random quantile level. You see here in equation number 2, the case where we work with the true law of the driving process y, and in equation 3, when we work with the false law of the driving process y. The difference between the two classes of random level quantile diffusions is a drift. So if we were to derive the differential equation for z in equation 2 and z in equation 3, we would see that the difference lies in a drift component. Manifestly, the quantile level of z is random. Obviously, we see that the quantile level is given by this process u, and thus it's a random variable at all times little t with according distribution. Over time, a random level quantile diffusion will produce scalar valued sequences of quantile levels, which correspond to the sequence of quantile values, which correspond to sequences of quantile levels. This is now the second type of quantile diffusion that we can construct, and it is function valued. Equation 4 is the definition for the function valued quantile diffusion, and we see that we take a generic quantile function q that depends on the quantile level little u. But crucially, it also depends on a set of parameters xi, and these parameters are modeled by multi-dimensional diffusions. So if we were to simulate this process z, the function value quantile diffusion, the quantile process will take values in a function valued space, because each realization at time t of the parameter diffusion xi will yield quantile processes over all quantile levels u in 0, 1. One thus obtains the entire quantile function as a realized observation, while zt, the quantile diffusion, provides the stochastic evolution of the entire quantile function. This is due to the fact that, unlike in the random level quantile diffusion, so the first construction, the quantile level u is not determined by the sample space, so by the sample element little omega. Let me now show you a class of quantile diffusions as an example, which is based on the Tukey quantile transform. This is a rather big class, and in fact, the Tukey quantile diffusions, Tukey quantile functions span the majority of the Pearsonian distributions. So the Tukey quantile functions are very flexible, and it's a family of transform maps which allow for the direct modeling, and this is important now, relative distributional properties such as skewness and kurtosis. So the transformation is always relative to some base distribution, as we shall see shortly. The distribution of a Tukey random variable is often characterized by the Tukey quantile function, which is another desirable feature of this class of quantile functions. We consider here two cases of a Tukey quantile diffusion, which are the Tukey G and the Tukey H quantile diffusions that are generated by the corresponding Tukey G-H transforms. And respectively, the Tukey G transform induces skewness, while the Tukey H induces kurtosis. So equation 5 is the definition for a Tukey G quantile transform, where A and B are constants in R and R plus respectively, and G is the parameter that controls the skewness relative to the normal distribution. So you see that XU is the probit function, so the quantile of the standard normal distribution. In the case of the Tukey H transform, H will control the kurtosis directly, and the corresponding quantile diffusion will be given in terms of equation 6. Note that in the case of the Tukey G transform, G may take values on the real line except at value 0, except value 0, and h usually is assumed to be positive. The reason being that one considers increased kurtosis, so positive kurtosis relative to the base distribution. Here I have a few plots. So the top two plots are the ones created by G-transform quantile functions that are generated for a range of G parameters. So on the left-hand side, you have positive G parameter, and on the right-hand side, negative G parameter, with respect to, so relative to, the normal distribution, which is the black line. In the bottom two plots, you have the H-transform quantile function, where you see how the kurtosis, the relative kurtosis, is controlled. And we've included here two exceptions, so where h is equal to minus 0.1 and minus 0.6, to show that for some values, for some negative values of the kurtosis parameter, the functions do not satisfy the conditions for a quantile function because they're not monotonic. In any case, it is natural to assume a positive h parameter. Here I'm showing you now as an example of a Tukey quantile diffusion, the Tukey G quantile diffusion, which is explicitly defined in equation 7, where the argument is this uniformly distributed process U sub little t, where we work with the true law of the driving process Y. We can compute the distribution, so the probability of the quantile Tukey G diffusion by equation 8, where we compute the probability of the driving process Y being less or equal to the quantile function Y that depends on time, and the Tukey G quantile function Fz. In the case that, so we've looked at two cases where the driving process Y is either geometric Brownian motion or the OU process, because we know explicitly the distribution or the law of those two processes, and we find that the stochastic differential equations for those two cases, in the case that we're working with the Tukey G quantile diffusion, are given by equation 10, dynamics 10. So the solution to 10 is 7 in the case where the underlying transform is a Tukey G quantile transform. I'm now moving to the applications. So we envisage several, but the first that jumped to our eyes once we discovered a paper by Godin et al., a recent paper by Godin et al., I'll have them included in the references at the end. It dawned on to us that these quantile diffusions could generate stochastic distortions of measures. And this is what I am going to show next. So we consider a valuation framework for assets and liabilities that are based, which are based on the distortion of cumulative distribution functions. So we consider a probability space omega fp with a random variable x that may represent, in a financial context, the financial risk, a financial risk that is distributed according to the function f sub x under the p probability measure. A well-known framework for distortion pricing is the Wang approach. And the Wang transform is defined in terms of a standard normal cumulative distribution function phi and a constant lambda, a real valued constant lambda. And this Wang transform induces a distribution distortion of the type as given in equation 11. So we see that the base distribution with which we begin is fp of the random variable x, which is then plugged in into the quantile function of the normal of a normally distributed random variable x, to which we add a parameter, a constant lambda, which in a financial context is usually interpreted as a risk premium. So the idea then was, and this is what I am going to show you next, is to explore distribution distortions that may have a flavor, as we see here, from the Wang transform, but which are induced by the stochastic quantile diffusions. Before I do show that, here is a plot for the Wang transform, where the plot shows you various functions, transform functions, for various levels of the risk premium lambda. And here we are including also the possibility for lambda being negative, which may be interpreted as a penalization. So here is how we construct distorted measures by using stochastic quantile transforms. We recall that the marginal distribution of a quantile diffusion that is constructed by the random level approach, so that would be the quantile diffusions of the first kind, is given by 12. And the way we now induce the distortion is actually stated in equation 13. So we consider a new measure P star, which is assumed to be equivalent to the measure P, in such a way that the distorted distribution, so the distorted measure P star of the driving process Y, is equal to the distribution, so the measure P, that the quantile diffusion process Z has under the measure P. So the focus is on using the quantile transformation of the driving process to reassign probabilities of outcomes under P to those outcomes that are realized under the P star measure. So naturally, the quantile measure transform defines a Radon-Nikodym derivative in the usual way, so defined in the usual way, as in equation 14, where the assumption is that the filtration in equation 14 is generated by the driving process Y. So the process Y of which distribution shall be transformed under the map generated by the quantile diffusion, the random level quantile diffusion. Associated with the Radon-Nikodym derivative, we can then also obtain the associated stochastic likelihood ratio that is given in 15. And you see that this is the usual ratio between the densities associated with the two probability measures. Here, I would like to emphasize that the Radon-Nikodym derivative that we see here, that is induced by the quantile transformation, is not necessarily the Girsonov transformation, where the transformation produces a shift in the mean. In fact, next, I am going to show you an example where the transformation, the measured distortion, is obtained by considering a 2-key GH quantile diffusion, meaning that under the transformation, there will be skewness and kurtosis generated, and clearly not of the type that would be otherwise generated by a Girsonov transformation. So the example I'm going to show you is one where at some arbitrary time, here 1/2, the P distribution of the driving process YT is plainly the normal distribution with mean mu times T and variance T. And the distortion will be performed by a 2-key quantile GH transform diffusion. So this is what will happen. So in the top line, so in the top two panels, you see in the left panel the effect, so the distortion for a range of positive skewness parameters G and the kurtosis parameter H. And on the right-hand side, top line, we have cases also including negative skewness. And these are for the case where the underlying driver Y is Brownian motion, so where we have no mean, zero mean. We also have two examples that are produced by the by a non-zero mean, so here assumed as being just 0.8, and of course we obtain a shift from the no distortion line, which is the 45 degrees line that you see here, where the shift is clearly visible. So the takeaways here are that the parameters in this distortion that come from the actual transform, here the 2TGH transform, control directly the effect that is observed through the transformation. And this can be very useful for all sorts of modeling questions and tasks. So I'd like to finish by mentioning a few projects that we envisage or maybe might be of interest to colleagues and beyond. So the first thing that we'd like to do is to extend the class of quantile processes beyond diffusions, of course, and the further development of function-valued quantile processes, which we believe actually to be quite interesting for a variety of applications. Then, so far, we've essentially worked, especially in the random level quantile diffusion setting, with univariate processes. So where Y is a univariate diffusion, we'd like to take that to a multivariate setting, and there are various ways that we think we can do it. Currently, we're working on numerics and numerical schemes for solving stochastic differential equations for quantile diffusions which do not have analytical solutions. And on the back of the application that I just shown you, that I've just shown you for the distortion of distributions, of course, there are others that may be related to pricing and risk management, particularly important for financial and actuarial questions. And with that, of course, once you have quantile processes, then it's just around the corner to set your eyes on dynamic risk measures and their development in a continuous time setting. So let me finish here by showing you the references, and if we have time, I'm more than happy to take any questions. Thank you very much for your attention.
Okay, thank you very much, Andrea. I don't see any questions from the audience right now. However, I have one question. When you talk about applications of these things, have you ever looked at S&P and VIX and tried to understand what kind of distortions are appropriate for modeling those two jointly?
Yeah. So, Jim, absolutely, absolutely in two ways. Absolutely not. We have not yet. We've been busy with actually producing this theory and understanding the two types of quantile diffusions that we generate. But of course, once you have classes of quantile diffusions that give you the opportunity to control higher order moments, then I think your question becomes very relevant, because actually when we began, the motivation, the main motivation for this work was to produce stochastic processes that would be very amenable to mimic statistical features observed in data. So I think your suggestion to look at S&P is a very good one, and so absolutely yes. If and when we get to the question of taking a data set and see what mimicking processes we could obtain by choosing a appropriate transformation, that would certainly be the interesting thing to do, and hopefully also the very fruitful application to pursue.
Okay, that sounds pretty exciting. And so thanks again for a wonderful talk, Andrea.
Thank you very much, Jim.
Yeah.